absolute value equation and optimization techniques. Actually, Shubham Kumar sir is currently pursuing his PhD in absolute value equation at PDPM, Institute of Information Technology, Design and Manufacturing, that is IIIT DM, Jabalpur, Madhya Pradesh, India, under the guidance of Dr. Deepamala. His thesis defense is scheduled on October 22, 2024. At this juncture, I congratulate Swam sir for the wonderful thesis and wonderful defense on that day, showcasing his significant contribution in the domain of solvability and applications of absolute value equations. Actually, he is also an active reviewer for reputed international journals, including Application of Mathematics, Stringer, Journal of Optimization Theory and Applications, Stringer, OP Search, Stringer, Sigma Journal of Engineering and Natural Science, Journal of Computational Applied Mathematics, Elsevier. His research work is widely recognized and publications in esteemed journals and contributions to mathematics modeling and computational methods. Today, he will be sharing his expertise on absolute value equations and their applications, a topic of immense significance in optimization problems, engineering, and computational mathematics. Without further ado, let us extend a warm welcome, virtual welcome to Dr. Shubham Kumar with a big round of applause. Sir, now the floor is yours.
Thank you so much, sir. It is great pleasure for me to present my talk with this wonderful session. Actually, this is also 30th anniversary of Salem Local Center, and the Institution of Engineers India. It is also established in 1920. And first of all, I want to thank Honorary Chairman Dr. K. Thangaraj sir and Honorary Secretary Dr. C. Dhavamani ma'am and all the member of Salem Local Center to give me opportunity to present my talk in this beautiful session. So should I share, sir, my PPT?
Yes, sir.
Okay, sir. Is it visible, sir?
Visible, sir.
Okay. Before starting our topic or our talk, first of all, I want a little introduction regarding me. So basically, I am Dr. Shubham. Completed my PhD in last year in from Indian Institute of Information Technology, Jabalpur. And after that, I September onwards, I joined as the assistant professor in Department of Mathematics at Graphicera Hill University, Dehradun, in Uttarakhand. And basically, I belong from a small town of Uttarakhand, which is situated in Pauri Garhwal district. So, for this 67th series of this the engineering talk, the topic of my today's talk is absolute value equation and its application. So let's see the content of the today presentation. So basically, this talk is divided in a certain chapter. We in chapter first we will discuss about this some introduction regarding the absolute value equation and some fundamental concept regarding the absolute value equation, how it is started and what is the literature review regarding the absolute value equation, what is the motivation to consider the absolute value equation. After that, in chapter 2, we discuss about the unique solvability condition for the generalized absolute value equation. And after that, in chapter 3, we will discuss about the unique solvability condition for the new class of absolute value equation. And in chapter 4, we extend the absolute value equation in for the metric equation. So in chapter 4, we discuss about the unique solvability condition for the absolute value metric equation. And finally, we conclude our discussion and some research problem regarding the future direction. We will see in the chapter 5. And then our talk or presentation will be ended with the references. So let's start it with the some introduction regarding the absolute value equation. So basically, in general, the absolute value equation is an equation where unknown variable within the absolute value operator. For example, simply mod x equal to 0 is an absolute value equation. Simply x have a restriction, it always positive, and we have to find the what value of x satisfy this equation. So you can see in the example one, we have a three different cases. So first we have mod x equal to 0. Second, we have mod x equal to 786, and in third case, mod x equal to minus 1729. So in each cases, we have, in first case we have unique solution. In second case, we have two solution. In third case, we have no solution. So this is the in general absolute value equation, but in research perspective, so we consider this absolute value equation. Ax minus mod x equal to b, which is given in equation 1. So basically, A is a matrix. It may be a square matrix or maybe rectangular matrix, but we considering here a square matrix. X is a column vector and B again is a column vector. So basically for given A and B, our target to find the unknown X, all the Xi values. So equation first is known as the absolute value equation in literature. The generalized version of equation 1 is known as the generalized absolute value equation, which is given in equation 2. So here A and B are given matrix. Again, we are taking here a square matrix and B is a column vector. For given data, our task to find the unknown X. So before starting to find the solution of it, we have a restriction on right hand side B column vector. So at least one bi not equal to 0. If it happened, then otherwise x equal to 0 will be the trivial solution. So for non-trivial solution, we have at least one bi not equal to 0. So before starting to main topic, we are see the some basic definition and basic definition of some more problem. So we start again from the linear complementarity problem. So basically the linear complementarity problem is defined as in a equation 3. So basically here we have a Z and WR column vector, which is non-negative, and W equal to Q plus MZ, and W transpose Z equal to 0. This condition is a complementary condition. So again here Q and M are given, and for these given data, our target to find the Z. And if we can find Z, then we can also find the W. So again here we have a restriction on Q column vector. At least one Qi should be negative. Otherwise, Z equal to 0 will be trivial solution. For non-trivial solution, we have Qi, at least one Qi negative. And the generalized version of this LCP known as a horizontal linear complementarity problem, which is given in equation 4. So if we are taking M1 equal to identity matrix, this equation 4 converted into the equation 3. And here for the HLCP, again, it have a same condition. For non-trivial solution, is Qi should be negative. Otherwise, Z equal to 0, W equal to 0, column vector will be a trivial solution. And in equation 5, we have a vertical linear complementarity problem, which is another generalized version of the LCP. So actually in further we will show the equivalent between absolute value equation and linear complementarity problem. That's why we are considering these definition. So let see the some literature what we have in literature. So basically Ziridon was the one researcher who in 2004 they considered this absolute value equation, generalized absolute value equation, ax minus b mod x equal to b, and they showed that this equation can be written as in this equivalent form, which is in given in equation 6, u plus is equal to inverse of a minus b, a plus b, u minus plus inverse of a minus b into b, where u plus and u minus are given that. So basically it is a one form of linear complementarity problem. That's why researchers are working on these equations, because linear complementarity problem already established field since 1950 onwards. And after that, Mangasarian further extend the work of Ronth. Uh, And they show that this absolute value equation ax minus mod x equal to b can be written as this form. A plus I into x minus b. It is a perpendicular to a minus I x minus b, and both are the non-negative. This is also a one type of complementarity problem. After that, Abdullah et al., Achache et al., and Majazri show that generalized absolute value equation can be written as an equivalence form of the horizontal linear complementarity problem. And further, Wu show that new generalized absolute value equation can be written as a vertical linear complementarity problem. And further, Kumar et al. Show that this equivalence relation between new class of absolute value equation and vertical linear complementarity problem. So let's see the what was the motivation behind the absolute value equation. So basically, absolute value equation have a many application optimization field, mathematical modeling, and engineering. So first motivation is it has a equivalence relation between linear complementarity problem, and linear complementarity problem is already a established field. Already the work is going 90-50 onwards on complementarity problem. And absolute value equation also applicable in variational inequality and mixed integer programming. And one more thing, it is basically it is a challenging NP hard problem because it is a non-differentiable and connection between the LCP and HLCP and VLCP, and these are the to find the solution of this equation is also a NP hard problem. And it is also related to the interval matrix system. So we have some point related to the motivation for the absolute value equation. So first one, basically this type of absolute value equation ax minus b mod x equal to b, it is an extension of this well-known linear system ax equal to b. So if we are taking here b equal to 0 matrix, then this easily can be converted into this system. So if we are studying this equation, then it is also useful for the understanding this linear system. Further, again, I am repeating, absolute value equation is equivalent to linear complementarity problem. Generalized absolute value equation is equivalent to HLCP problem, and new generalized absolute value equation is equivalent to vertical linear complementary problem. So the equivalence gives us a new perspective for each problem. Maybe some problem is tough to solve in LCP, so we can convert it into the absolute value, then we can solve in the absolute value equation form. Further, it is the absolute value equation is also used closely related to this interval matrices. And the absolute value equation is also can be equivalent to the 0-1 knapsack feasibility problem, and it is also can be formulated like these problems 0-1 knapsack feasibility problem and set partitioning problem can be formulated as the absolute value equation and generalized absolute value equation. And further, when we are solving some differential equation system or some differential equation model, then absolute value equation also arise. For that, we can see the reference number 6, where the free surface hydrodynamics problem and flow in porous media we can see in this reference number 7 and 10. And the absolute value equation also arise in the when we are dealing with the boundary value problem, which can be seen into the reference number 41 and 63. And one more thing, the absolute value equation is also connected with the variational inequality problem and optimization problem, in particular linear programming problem. So basically LPP problem can be converted into the LCP problem, and LCP problem can be converted into the absolute value equation. So, and also it is connection with the mixed integer programming problem. So now let me see some literature review regarding the absolute value equation. So basically, Ziri-Rohn was the first researcher who considered this absolute value equation in this form ax plus b mod x equal to b, and he introduced the theorem of alternative for its solvability. After that, many researchers give some different condition to find the solution of this absolute value equation. Solution in the particular unique solution. Okay, so in the literature, these different type of absolute value equation are considered. First one is absolute value equation. Second one is generalized absolute value equation. Third one is new generalized version of the absolute value equation. Fourth, we have a new class of absolute value equation, and similar with triple absolute value equation, extended version of the absolute value equation. All these absolute value equation are can be summarized in the following table. So basically, this was the first absolute value equation which was considered by the Ziron in 2004. After that, many researcher in 2006, 12, 21 and consider the different type of absolute value equation. So recently we consider this absolute value equation ax minus b mod of cx minus d is equal to b, which is the extension version of the all the previous absolute value equation except 3 and 7. But in this presentation, we consider this absolute value equation. Actually, we provide some new unique solvability condition for this equation, second one for this equation, and this new class of absolute value this equation ax minus mod of bx minus c equal to b. Unfortunately, we not provide the absolute unique solvability condition for this equation in this presentation. So further, we will consider the unique solvability condition for first one, second one, and fifth one. Sorry, sixth one. So basically, regarding the absolute value equation, the research going on 2 and 3 direction. First one is theoretical study where researcher are providing in which condition this absolute value equation has a unique solution. And another is researcher providing the numerical method to find the solution of these absolute value equation. So basically, when absolute value equation system is solvable, it may be a unique solution or many solution. When multiple solution exist, then due to the optimization problem, then right one solution is crucial for the various practical application. So that is why several researcher is working on the unique providing the unique solvability condition. Hello?
Sir.
Yes, sir.
Yes, sir.
Sir, my PPT is visible?
No, sir.
Ma'am, is my PPT visible or not?
Not visible, sir.
Actually, I think I lost my internet connection from laptop. 1 second, ma'am. Ma'am, is it visible from my mobile?
Still not visible, sir. Chairman, sir, is it visible? For me, not visible.
No, ma'am.
Actually, ma'am, I lost my Wi-Fi connection from my laptop. So I am sharing from my mobile.
Mobile, okay, sir.
My PPT is visible or not?
Sir, I think not visible. Chairman, sir, is it visible, sir?
No, not visible, ma'am.
Not visible, not visible.
1 second, ma'am. Ma'am, currently, is it visible?
Yes, sir.
Yes, sir, now
It's
visible.
visible, sir, now.
Okay, ma'am. Actually, ma'am, I am presenting from my mobile. Actually, I lost Wi-Fi connection in my laptop. That's why I'm presenting from my
Okay, sir.
mobile.
No problem, sir. Please proceed, sir.
1 second. So, Jerry Rowan was the first researcher. We are currently in the slide number 13. So, Jerry Rowan was the first researcher to provide the first research regarding the unique solvability of the generalized absolute value equation. And due to their huge contribution in absolute value equation, Jerry Rowan also known as the father of absolute value equation. Further, the terminology absolute value equation was given by the Mangasarian in 2007. And further, in the singular value condition, sigma mean a is sigma mean a greater than one was initially established for the unique solvability for the absolute value equation one. Okay, sigma mean a means is minimum single value of matrix A if strictly greater than one, then our absolute value equation has a unique solution. Here singular value means suppose you have a matrix A and matrix A given, so we are calculating the eigenvalue of A into A transpose. Suppose it have a lambda eigenvalue, then we are taking square root, then which after taking square root, which is a minimum eigenvalue, which is the sigma mean A we are denoting here. After that, Rowan extend this condition for the generalized absolute value equation, and he present the condition sigma min A greater than sigma max mod B. If this condition satisfied, then absolute value equation has a unique solution for each B. After that, again, Wu et al. Refined the previous condition and show that if sigma min A greater than strictly greater than sigma max B, and another condition was proposed if sigma max A inverse B less than 1, then again absolute value equation has a unique solution. Actually, the current condition sigma max A inverse B is less than 1 is a superior the all the previous condition. So after that, Ron derived the another spectral radius condition for the generalized absolute value equation 2, which is given if spectral radius of modulus of A inverse B is strictly less than 1, then again absolute value equation has a unique solution. And similarly, another researcher provided a different type of absolute value equation. For example, Wu et al. In 59 show that if spectral radius of A inverse B into sorry. 1 second, ma'am. Wu et al. In 59 proposed another condition. If spectral radius of A inverse B into D bar is strictly less than 1, then again generalized absolute value equation has a unique solution. Basically here D bar is the diagonal matrix whose entry belongs from the minus I to plus identity matrix. So next, Hladik investigate the topological property of the solution set for the absolute value equation. Included, they investigate the boundedness of the solution set, connectedness, non-negativity, finiteness, and convexity of the solution set of the absolute value equation. After that, Wu et al. Using from the spatial matrices, they provide the condition 7. If this condition 7 satisfies, then again absolute value equation has a unique solution. And Wu et al. Give the necessary and sufficient condition based on the interval matrix. So the absolute value equation has a unique solution for each B if and only if this interval matrix system A minus In A plus In is regular. Basically here In is the identity matrix of order n, and like we have a interval 0 to 1 number, so similarly we have a interval matrix. Here all the entries are in matrix form. If all the matrix belong to this interval matrix is invertible, then we said that this interval matrix is regular. So basically, recent survey and recent paper regarding the survey paper regarding the absolute value equation can be found in the reference number 1 and 2.
which is the recently one of the paper is recently published, and one of the in the also can be found in the archive version. And in numerical method, there is a various numerical method also present for the solving absolute value equation. So we have optimization approach, Newton type method, Picard type method, SOR like iteration method, and other different type of method to solve these absolute value equation. So basically in this talk we focus on the unique solvability condition for the find the solution of the absolute value equation. We don't focus on the numerical method for the solving absolute value equation. So in chapter 2, we discuss about the unique solvability condition for the generalized absolute value equation. So basically in this chapter, we discuss about the some unique solvability condition and solvability condition for the generalized absolute value equation ax minus b mod x equal to b. Further, we give the possible revised version of the unique solvability condition of the two incorrect results that are appeared in the published paper by Wu et al. Of 2018. Further, we also give some counter example and sub alternative result of the published result of the Wu et al. In 2016. So basically, this chapter is the part of these papers, which is in 1 and 2 form. So before starting the main result, we start from some basic definition. So for example, we have a matrix A and delta, and we have a condition on delta. All the entries of matrix delta is greater than or equal to 0. Then we are making an internal matrix IA, and it is A minus delta, comma A plus delta. It is said to be regular if each k belong to this interval matrix is invertible. If we will find any k matrix which is not invertible, then this internal matrix IA is singular. Second, we have suppose a matrix A is categorized as a non-singular M matrix if and only if we have a matrix delta which is greater than equal to 0, and we can express our matrix A in the form of gamma in minus delta, where gamma is a number which is strictly greater than of the spectral radius of matrix delta, and the same matrix A is said to be H matrix if and only if its comparison matrix is non-singular M matrix. So now let's see some main result. So first we will see some unique solvability condition for this equation ax minus b mod x equal to b. So in theorem 4 we have a condition 8. If we have a square matrix A and B, and this satisfies the condition 8, then our generalized absolute value equation has a unique solution for any B. So we compare our condition with some existing result of the literature. So in theorem 5 we have some existing condition. So in first we have if sigma max mod of B is less than by the sigma min A. Second we have if sigma max B is less than sigma min A. And third condition we have is if A transpose A minus 2 norm of B square I is a positive definite matrix. And fourth condition, if all these four conditions is satisfied, then generalized absolute value equation 2 has a unique solution. So first we will compare our condition 8 with these four conditions. For this we are considering example 6. So here we are taking this matrix A, 2 by 2 matrix. Suppose these have these anti 1.0200 and 1.2003, and we are taking matrix B which have minus 0.8999 and like that similar way, and we are taking this particular B we have minus 0.5429 and 6.727. So here our condition given in equation 8 are clearly satisfying here, but when we are trying to when we are applying condition of theorem 5, so here all the four conditions are not satisfying here. First we can see that sigma min A not strictly greater than 1.0276, which is sigma max B, and similarly sigma min A also not strictly greater than by sigma max mod B. And again A transpose A minus 2 norm of B square I is also not a positive definite matrix because it is containing the negative eigenvalue. Similar way another A transpose A minus 2 norm of mod of B square into I also not a positive definite matrix. So in this example, we show that our condition is satisfying, but existing condition is not satisfying here. Next, again we are considering two more condition from the literature, which is can be seen in the theorem 7. So hello, sir, my voice is audible or not?
Audible, sir. Audible, sir.
PPT is also okay, ma'am?
Visible, sir. Visible.
Okay, thank you, ma'am. So in theorem 7, we have a two more condition regarding the unique solubility of the generalized absolute value equation. If this first and second condition are satisfied, first one is singular value condition, second one is a spectral radius condition, then again generalized absolute value equation have a unique solution. So again we are comparing our condition, this is given in equation 8. We are again comparing our condition 8 with the condition of theorem 7. So for this, we are considering the example 8. Here A equal to, we are taking a tridiagonal matrix which have -1, 8, -1, and we are taking B equal to identity matrix, and here n is greater than or equal to 3. So again here our condition of the theorem 4 is satisfying here, and also these two conditions also satisfying here, but we are computing the CPU time. For this we have this table. So when we have a three condition, 1 and 2 are condition are given in literature, and third one is condition 8 was our condition. So when we are taking the size of matrix is 1000, then first and second condition are taking this time, first condition are taking 0.12 something, and second condition are taking time 0.24 something, and but our condition are taking very less time comparing to other two condition. Similar way, when we are increasing the size of matrices, for example 2500, 5000, or 7500, or 10,000, then each case our condition are very taking very less time compared to previous two condition. So one advantage of our condition is that our condition is taking less CPU time. Now next we will see some more result regarding the unique solubility of the general absolute value equation. So for in theorem now we have one more result. If B is greater than or equal to 0 and A minus B is an M matrix, then again this equation has a unique solution. Similar way, if A minus B is an H matrix with positive diagonal element, again this equation has a unique solution. In theorem 11, for example, if this satisfying certain condition like B is greater than or equal to 0 and it is symmetric, A is positive definite, and this condition is satisfied x transpose AX minus mod of x transpose B mod x is greater than 0, then again this have a unique solution. Now we will see some unsolvability condition for the gap. So in theorem 12, if this condition satisfy, which is given in equation 9, and we have some restriction on B inverse B. Actually B inverse into B not exactly 0, it have a symmetry which is greater than or equal to 0, then generalized absolute value equation has a no solution. And equation 9 can be written as in equation 10 and 11 form. Is these two condition given in 10 and 11 also satisfied, then again generalized absolute value equation has does not have a solution. Now let's see the next result. We are in this we are considering the absolute value equation in form of Ax minus mod x equal to B. So basically we can see in the reference 55, Wu et al. Give the following two result, which is given in theorem 13 and theorem 14. If these two conditions are satisfied, then they claimed that the absolute value equation have a unique solution. So further we show that these both the result are incorrect. For theorem 13 and 14, we are providing the counter example. For theorem 13, we are giving the example 15. Here all the condition of theorem 13 are satisfying, but the corresponding absolute value equation not have a unique solution. Actually, it have a two solution. Similar way, for theorem 14, we are giving the example 16. Again, it have a not unique solution. Suppose we are considering, suppose f1, f2 is 1 and 15, then this absolute value equation no solution. If you are changing our f, for example, it is 0, 0, then it has infinitely many solution. So further, we give the potential revised version of the theorem 13 and 14. So the revised version of the theorem 13 can be seen in a theorem 17. So if A is be a symmetric matrix and all the eigenvalue of A not lie in this interval -1 to 1, then absolute equation has a unique solution. And the revised version of the theorem 14 is given in the theorem 18. So if let matrix A be a positive definite and H and S be its Hermitian and skew Hermitian part, if the smallest eigenvalue of the matrix H is larger than 1, then absolute equation has a unique solution for every B. Next, we have another two result regarding the unique solubility of absolute value equation. So basically, this result was presented by the Wu et al. In we can see in the reference number 56 in 2018. So they provided these two conditions, which is given in theorem 19, first and second. Also, but Haladi et al. Shows that these conditions are incorrect. If we are taking matrix A, all the condition of theorem 19 are satisfying, but the corresponding absolute value equation minus x equal to b. If we are taking b as a positive, then this condition, then absolute value equation does not have a unique solution. So, but Haldik et al. Not provide any revised version of the theorem 19. So this motivates us to derive the following result, which is given in theorem 20. So we restrict the bound of the right hand side bound of this condition. In initial it was the strictly less than by 2. We restrict it is the strictly less than by the 1 by 2. So theorem 19 can be replaced by the theorem 20. So basically in this chapter we discuss about the unique solubility condition for the generalized absolute value equation, and further we also provide non-uniqueness condition, and further we identify the some incorrect result from the published paper of the literature, also provide the some revised version of the incorrect result. So next, in next chapter we have a unique solubility condition for the new class of absolute value equation. So basically we consider the equation 12, which is known as the new class of absolute value equation, ax minus mod of bx minus c equal to b. So basically when we set is, for example, b equal to identity matrix or c equal to 0 column, actually b c are the column vector, x is also column vector, a and b are a matrix. Again here x is unknown, all the other data are given. So if we are taking some particular choice of B and C, so this equation can be also reduced to some existent absolute value equation. So we provide the unique solubility condition for the equation 12. So again we have some definition. So a matrix A is a P matrix if every principal minor is positive. And next we have a definition if let fancy M equal to Mn and M2, we have a set of two matrices. It is the so a matrix R is said to be row representative of this fancy M if here Rj dot, that means jth row of R matrix is belong to the either jth row of M1 matrix or jth row of M2 matrix. And similar way column representative we have if jth column of R matrix belong to the jth column of M1 matrix or jth column of M2 matrix. And further we have another definition of row or column W property. So the set M hold the row or column W property if the determinant of all the row or column representative matrix of M are positive. Now let we recall the definition of vertical linear complementarity problem, which is given in 14. So if gx plus p is greater than equal to 0 and hx plus q is greater than equal to 0, if a complementary condition gx plus p transpose into hx plus q is equal to 0, this problem is known as a vertical linear complementary problem. So basically here x is unknown, p, q and g and h are the we have given. So first we show that in lemma 25 our the new class of absolute value equation can be written as in the form of 14, which is given in equation 15. So basically new class of absolute value equation is identical to the following vertical linear complementarity problem, which is given in equation 15. So based on the equivalence, we utilize the vertical linear complementarity problem, the result of vertical linear complementarity problem, to derive the unique solubility condition for the our absolute value equation 12. So same way we have a theorem 26 and theorem 27 to give based on the row W property and column W property, which give the unique solubility condition for the new class of absolute value equation. Similar way in theorem 28, based on the spectral radius, which is given in equation 16 in equation 17, and based on the singular value condition, which is given in equation 18 and equation 19. If these conditions are satisfied, then our new class of absolute value equation has a unique solution for any right hand side B. And similar way, based on the strictly diagonal dominant by columns and irreducible diagonally dominant by column, we have a theorem 29. And based on the interval matrices, we have a theorem 30. If this interval matrix AB inverse my I and AB inverse plus I is regular, then our absolute value equation 12 has exactly one solution. And in theorem 31, we have a based on the P matrix. If the matrix A minus B into A plus B inverse is a P matrix, then again our system has a unique solution. In theorem 32, we have a if matrix A plus B minus 2 dB is non-singular, where D belong to the, actually D is a diagonal matrix whose diagonal entry belong to the between the 0 to 1, then our system has a unique solution. So basically in this chapter we consider the new class of absolute value equation Ax minus mod of Bx minus C equal to B. So basically it is a generalized version of the new generalized absolute value equation Ax minus mod of Bx equal to B, and this absolute value equation Ax minus mod X equal to B. Some necessary and sufficient result we also obtain and some earlier work of 56 and 58 are generalized here. Further, we get some new result, new unique solubility result for the new generalized absolute value equation 13. Basically, these results are not covered by the paper of Wu, which can be seen in the reference number 58. Now, let's see the chapter 4. So here we extend our discussion for the metric equation, particularly absolute value metric equation. So basically we consider the metric equation in form of Ax minus V mod X equal to B. Basically we are considering in previous discussion we are considering the X as a column vector and right hand side B as a column vector. But here we can see that Ax minus V mod X equal to B, all are the matrices. Here A, B and F are given. For given matrices, our target to find the unknown X. So we are considering the absolute value metric equation which was given in 20. So basically it is the generalized version of the this generalized absolute value equation Ax minus B mod X equal to B. Just one difference, here X is a vector form, column vector form, and here X is a matrix form. So let's start it from the main result. So basically Degan et al. And K. Zhai provide the condition 21 and 22 for the unique solubility of the absolute value metric equation, which can be seen in the theorem 33. So we provide the another condition which was given in 34. If maximum single value of matrix A inverse B is strictly less than 1, then absolute value metric equation has a unique solution for any matrix F. So basically we compare our condition with the 21 and 22. So basically our condition is superior to the these two conditions, 21 and 22. For this we are considering the comparison in this note. So based on the relation of the single value condition, we can see that it can be derived it is the superior condition. For further we considering the example 35. Here A is a matrix, B is a matrix, and again the condition of the condition of the theorem 33, both condition 21 and 22 are not satisfying here, but our condition 23 satisfying here. Next we have some more condition. For example, actually the condition theorem 36 was presented in the reference number 54. So if this condition satisfying spectral radius of, it is actually canonical delta product of matrix I and A inverse B, and it is a gamma bar. If it is a strictly less than 1, then again absolute value metric equation has a unique solution. So further in theorem 37 we are providing the another condition. If spectral radius of A inverse B into D bar is strictly less than 1, then again absolute volumetric equation has a unique solution. In theorem 38 we have another result. So if either of condition first or second satisfy, then again absolute volumetric equation has a unique solution. For the application of theorem 38 we are considering the example 39. So we are simply considering the simple matrix. Suppose A is the 2 times of identity matrix and B is the identity matrix. Then again the both two conditions are satisfying and it has a unique solution. In theorem 40 we have a result if the absolute volumetric equation alpha times ax minus b mod x equal to b, here mod of alpha is greater than equal to 1, if it has a unique solution, if and only if absolute value equation ax minus b mod of x equal to f has a unique solution. And further we are giving a one remark or one future open question research problem. If is the unique solvability of absolute value matrix equation preserved under the matrix transformation, that is if this equation has a unique solution ax minus b mod x equal to f can be unique solvable for each f, then if we are taking transpose of matrix A and B, that is A transpose X minus B transpose mod X equal to F, it is also uniquely solvable for each F or not. This needs basically further investigation. So further we have some condition regarding the unsolvability of our absolute value matrix equation 20. So if 0 is not an eigenvalue of matrix B and if it is not identically zero matrix or it may have some greater than or 0 greater than or equal to 0 entries, then if this condition satisfies sigma max B inverse into sigma max A is strictly less than 1, then our absolute value matrix equation has a no solution. In support of theorem 42 we can see the example 43. Here we are taking matrix A, B and F. So clearly the condition of the theorem 42 are satisfying here. So this absolute value matrix equation does not have a unique solution for this given F. So basically in this chapter we discuss about the unique solvability of the absolute value matrix equation. We also discuss about some unsolvability condition. So further exploring the numerical method for the solving the absolute value matrix equation is an interesting area for future research. So in next chapter we have a unique solvability condition for a new class of Sylvester like absolute value matrix equation. It is a another particular type of matrix equation. So basically we are considering Lee consider this equation 25 axb minus mod of cxd equal to f and he give its name Sylvester like absolute value matrix equation. So we further investigate provide some new condition for this equation. So basically Lee in 2022 consider this equation provide the unique solvability condition. After that 2023 we provided some new condition for the unique solvability this equation. So first in theorem 44 based on the interval matrix, if this system of interval matrix is regular, then again absolute value matrix equation system 25 has a unique solution. And similarly if we have a theorem 45 and 46, in 46 we have it is related to the spectral radius condition. If this condition is satisfied then again it has a unique solution. Next in theorem 47 and 48 based on the column W property and row W property we have a result in theorem 47 and 47. If any one condition from in theorem 47 if any one condition from 1 to 6 is satisfied, then our system 25 has a unique solution. And same way in theorem 48 if any condition from 1 to 5 are satisfying, then again our system has a unique solution. And basically the condition in given the condition of theorem 49 was given by the Lee in 28. If this condition sigma max C into sigma max D is strictly less than sigma min A into sigma min B, then system 25 has exactly one solution. So basically we provide some superior condition which is given in theorem 50. For this we are considering this example. Suppose we have some given data A, B, C, D and F. So clearly the condition of theorem 50. The condition of theorem 50 are satisfying here, but the condition of given in theorem 49 is not satisfying here, which was given by the Lee in 28, and but it has a unique solution which is given in form of X. So basically, in this chapter, we consider the new class of Sylvester-like absolute value metric equation, which have a form AXB minus mod of CXD equal to F. Again, I am repeating here, A, matrix A, B, and C, D, and F are we have given. For given data, our task to find to the unknown matrix capital X. So we also provide the some new condition which was not covered by the in previous paper. So further, the numerical method for the solving this class of Sylvester-like absolute volumetric equation are also an interesting topic for the future. So in last chapter, chapter 6, we conclude our discussion with some raise some future direction. So basically, in this presentation, we discuss about the different type of absolute value equation and some generalized version of these absolute value equation. So in chapter 1, we recall some basic definition and some we see the some motivation behind the absolute value equation and some literature review regarding the absolute value equation. Further, we in chapter 2, we discuss about the unique solvability of the generalized absolute value equation, and in chapter 3 we discuss about the unique solvability condition for the new class of absolute value equation, and in chapter 4 we discuss about the unique solvability condition for the absolute value metric equation, and in chapter 5 we discuss about the we derive actually new unique solvability condition for the new class of Sylvester-like absolute value metric equation. So so let's see the some future direction of the absolute value equation and absolute value metric equation. So researcher actually now currently working on the tensor absolute value equation, which is another generalized version of the matrix equation. It is like, suppose we have a column vector. So matrix is a one type of generalized version of the column vector, and tensor is a one type of generalized version of the matrix. And further, the new new generalized absolute value equation and new class of absolute value equation was introduced in 58 and reference number 24. But best of our knowledge, there are not many numerical method to solve these type of equation. So one may interested one can work on this equation to providing the some numerical method to find the solution of these type of equation. So in the literatures, several open problem also remain unsolved related to these absolute value equation. For example, we can see these open problem in reference number 20, 21, and 25. Some of the open problem we are mentioning in the next section. So for example, we have some 4 to 5 open problem. So first one is actually sufficient condition are too easy to apply compared to the necessary and sufficient condition on the absolute value equation. So first open problem is related to the sufficient condition. So modifying the sufficient condition to become necessary and sufficient condition would be a significant contribution. However, it may be extremely challenging because absolute value equation is an NP-hard problem. So, and second open problem is can absolute value equation, the unique solvability of absolute value equation for every non-negative right hand side vector B implies the unique solvability of this absolute value equation AX plus mod X equal to B for every B belong to the B is a column vector. Third open problem we have, does the fact that the equation AX plus B mod of CX equal to B has a unique solution for every B also mean that the system AX plus B mod of CX minus D equal to B has a unique solution. And fourth open problem we have regarding the unique solvability of tensor absolute value equation, a complete characterization of the necessary and sufficient condition is still unknown. And last open problem we have last open problem we have, the each unique solvability condition of AX minus B mod X equal to B is also applicable to the check the unique solvability of this absolute value metric equation AX minus B mod X equal to F. So these are the some open problem in the literature, and these are the references which I used regarding this presentation. And thank you to everyone to listening to my talk. Thank you to everyone.
Yeah, thank you, Subham. It's a wonderful session. Actually, I have one question. So, where we can apply these again equations in our machine learning, like other again components.
Sir, actually, the absolute value equation is equivalent to the linear complementarity problem and linear programming problem. So basically, regarding the machine learning, sir, I have not exact idea. It may be applicable or maybe not applicable. Actually, I have not exact idea in the field of machine learning or artificial intelligence. But one thing, it is actually NP hard problem. Maybe there is some possibility to apply to application in the machine learning, but I am not sure, sir.
Okay, thank you. Audience, the floor is now open for the queries. If anyone having any query regarding the topic, please now. Our guest is again waiting for your questions. Okay, participants, you can take your own time. We share our today's guest email ID and contact number. If you have any query, you can also approach through mail and phone number also. Thank you, Shubham. So now I request our Honorary Secretary, ma'am, to propose vote of thanks.
Thank you, sir. Sir, I am audible, sir.
Yes, ma'am.
Our most respected, our chief guest and keynote speaker, Dr. Shubham Kumar, sir. Our beloved chairman, Dr. K. Thangaraj, sir. Respected participants from local center and state center and other colleges, other organizations and students. Good evening to all. I am very much happy to propose vote of thanks on this great occasion. Special lecture under the aegis of IEI Interdisciplinary Coordination Committee. This is the 67th topic. The title is Absolute Value Equations and its Applications. On behalf of IEI Salem Local Center, I extend my sincere thanks to our chief guest and keynote speaker, Dr. Shubham Kumar sir, IIIT DM, Jabalpur, for delivering such an insightful and engaging presentations. Actually, sir, your expertise and clarity in explaining the concept of absolute value equations and their real world applications have undoubtedly deepened our understanding of this important mathematics topic. Thank you, sir. My sincere thank you, sir. My sincere thanks to our beloved chairman, sir, Dr. K. Thangaraj, for his hard work in planning and executing this seminar successfully. I extend my sincere thanks to our engineers talk team series, Dr. R. Satish Kumar sir, Dr. A. Kumaravel sir, Engineer N. Arumugam sir, Engineer K. S. Selvam sir for their continuous guidance and support. I record my sincere thanks to Thiagu for his wonderful coordination. Thank you, Thiagu. Finally, I heartfelt appreciation to all the participants. Your participation made this session more meaningful. Once again, thank you to all. Thank you, Shubham sir. Thank you, Chairman sir.
Thank you, ma'am. Shubham sir, thank you.
Thank you so much, sir. It was a great session. And